Welcome back, physics people. We are in chapter 14. This is part 2. Be sure that you see part 1. This is part 2. We'll be breaking the chapter into maybe 4, possibly 5 parts. Beginning with part 2, we're going to start doing something new, and that is this. To help me verify that folks are actually watching the videos, I'm going to embed, provided I don't forget, I'm going to embed at various points in the discussion of Chapter 14, Part 2, 4 quiz questions. Those 4 quiz questions will be very simple little things, very simple. And here's what you're going to do. Write them down as we go. And then what I want you to do is send me an email. Do not take a picture of your answers and email the picture to me. I'm getting like 80, 85, 90 emails a day from homework assignments, and that's just unmanageable, especially if I have open pictures for each one. So for these quizzes that I'm going to be giving for physics, I want you to just send me an email with the following subject line: Physics Quiz 14 Part 2, or perhaps just Phys Quiz 14 PT2 to save space. I like this because I know that that'll fit easily on my compressed email screen. That's all I want in the subject line. And it just occurred to me, for my Ch14 students only, since this video will be seen by both Ch14 and by Covenant Life. Ch14, if you could put in the additional CI designation there, so I can sort these things out more easily. In fact, anytime you communicate with me, I have had some confusion already with folks sending me things, and I don't know if it's CLS or CI. So if you're a Ch14 Institute, please put CI in the subject line also. What I want you to do is simply send me a text, not a text, send me an email with the 4 quiz answers in the body of the email, typed into the email itself. Don't take a picture of your answers, please. Just type them into the email. That way all I have to do is go click, good, and you get your score. It'll be 4 points for each quiz, 1 point per question. So I'm going to start doing that on a regular basis, provided I remember to do it. That's debatable. Okay, so I'm on page 270. And first of all, just a quick review, very quick review. We know that air actually does, contrary to what a lot of folks in this world probably think because they're uneducated, we know that air has weight. Why does air have weight? Because it's made of matter, molecules. The earth is attracting them gravitationally. They're being held back by the surface of the earth. There's a support force. Air pushing on ground, support force, it has support force, it has weight. Air has weight. More weight than we think. Remember I mentioned last time, not yesterday, that's right. I mentioned last time that, as Paul Hewitt says, the air in your little sister's bedroom weighs more than she does. 1 cubic meter of air weighs about has a mass of about 1 1/4 kilograms. That's surprising, but true. Now, important to note, and here we begin page 270, important to note that as we go up in the atmosphere, think about this, the higher you go, the less air you have above you, right? So the higher you go, the less air pressure there is. You go, in fact, Paul Hewitt mentions that if we go up to an elevation of 10 kilometers, go up 10 kilometers, the air pressure is all the way down to, okay, doesn't detail us here. The weight of the air in 1 cubic meter at that altitude. Remember, here at sea level, 1 cubic meter, about 1 1/4 kilograms. At 1,000 kilograms up, at 10 kilometers up, the weight of that same cubic meter of air is only about 0.4 kilograms. Because there's less of the air in that box. Same size box, but it's more spread out. That's why a jet airliner has to pressurize the cabin. As they're flying at these high altitudes, there's not enough air pressure up there to sustain human life. There is some air pressure, certainly. A plane can't even fly without air. But there's not enough air for us to survive in it. So the cabin of the plane has to be pressurized. While we're down here on the earth, why don't we feel all this pressure on our bodies? Remember, I believe I mentioned the last time that every square inch of your skin has 15 pounds of air pressing against it. So again, another way that Paul Hewitt looks at this, why don't we feel that pressure? Well, does a fish feel water pressure? No. If I have a water balloon in my hand, I feel the weight of that water balloon. But what if I take that same water balloon and put it in water? All of a sudden, it doesn't have any weight at all. I'm kind of like that water balloon in the water. I live in the air. I don't notice the pressure. This is where I live. I have the same pressure inside and outside. I don't feel the pressure. But believe you me, if we took that pressure away, then you would feel it. Yeah. In fact, just driving up into the mountains, going up a hill into the mountains, you feel your ears pop. What's that all about? You go up in a mountain, even a small mountain, just go into West Virginia, go up into the mountains there. And you're going a little higher. As you go higher, there's less air above you. The air pressure is a little lower up there, enough so that there's less pressure on your eardrums. You still have the regular 15 pounds per square inch inside you, but now you have less than that outside. So your eardrums start to go as your inside pressure is pushing out against the low outside pressure. And that doesn't feel good, and it makes things sound funny. Then you kind of, you do this stuff, or yawn or chew gum or something, and you hear a pop, and then it feels better. What's that all about? You're opening up your eustachian tube. That tube that goes from your inner ear to someplace in your throat, your nasal area. I don't know the biology, but you have managed to open up that tube and allow the higher pressure inside your ear to equalize, and it goes back to normal. So now the inside and outside are equal. You hear the pop, and it feels better. Then you go back down, home again, and the outside pressure gets greater. Your eardrums start to do this. So then you open up those eustachian tubes, and you get another pop, and it goes back to normal again. You're equalizing the pressure between the outside and the inside. Okay, so as you go up, pressure gets less. He also mentions that if you have a bamboo pole, what's special about a bamboo pole? A bamboo pole is hollow on the inside. Pretty cool. If you have a bamboo pole, he says, and we've got the earth here, and we've got this bamboo pole, a really, really tall bamboo pole, a bamboo pole that goes all the way up to the top of the atmosphere, wherever that may be. A bamboo pole to the top of the atmosphere. He says that that bamboo pole would contain about 10 newtons of air, about 1 kilogram of air. It would weigh about 10 newtons. Now, here's the interesting thing. If you take that and multiply by enough of those square centimeters, we're assuming that inside a bamboo pole you have about 1 square centimeter of area in there. If you take that 1 square centimeter and multiply it out over an entire square meter, get this. In 1 square meter, when you're on the ground, you would find that above you, from there to the top of the atmosphere, you will have about, about 10,000 kilograms of air. You have the weight of 10,000 kilograms of air from the top of the atmosphere to the ground, pushing down on every square meter of area on this floor. 10,000 kilograms. That has a weight of 100,000 newtons. 100,000 newtons of weight of the air pushing on every square meter of this floor. Well, why doesn't it crush the floor? The floor is pretty tough. What about why doesn't it crush the ceiling? Well, because there's not only 100,000 newtons of air pushing down on the ceiling, that same pressure, Pascal's principle, earlier chapter, that same pressure is also pushing up on the ceiling. Everything cancels out, nobody cares. In terms of pounds, for those who don't like talking about 100,000 newtons, what does that mean? In terms of pounds, 1 square meter of floor space is holding up 22,482 pounds of air. 22,482 pounds of air on every square meter of floor space. But you said a square meter only weighed about 1 1/4 kilograms, only had a mass of 1 1/4 kilograms. Now that's just the air in that 1 square meter. We're not talking about the weight of the air from the ground all the way to the top of the atmosphere. That's a whole lot more than just 1 cubic meter. Yeah, 1 cubic meter is only about 1 1/4 kilograms. But multiply that by the height of the entire atmosphere, and yeah, you're talking about a whole bunch of air. Okay, let's see. Oh, and that translates, by the way, down to, on 1 square foot, about that big, you have 2,160 pounds. That's about 1 ton of air on every square foot of area on the floor. Like, wow. Now, we could measure the air pressure by doing this. Suppose we had a pan of water, and we have a jar, kind of like in that demonstration I showed you earlier. If we had a jar of water that is 34 feet high. Now let's make it 36 feet high. Here to here, 36 feet. That's a really tall jar. If we fill that thing with water, as was mentioned earlier in the demonstration I showed you, the atmosphere around us is heavy enough to hold up 34 feet of water. So if this whole thing is filled with water, that thing could be filled all the way up here to 34 feet, and the atmosphere would hold it up. What if you tried to put 35 feet in there? Well, you can't. You put 35 feet in, it's going to slide right back down to 34 feet. What if you put less than 34? You put less than 34, it's going to rise up to 34 feet as the air pressure pushes on this surface, and that air pressure is transmitted up here. It will support 34 feet of water. Doesn't even matter whether this tube is skinny or large. It'll hold up 34 feet of water. Hey, by the way, what would happen if we took that same 34-foot tube and laid it down like this so that it's lower than 34 feet? Well, then, it's kind of cool. What happens is the whole thing would fill up with water. Then as I tilt this up, when the tip of that tube comes up here above the 34-foot mark, what happens? The water will slide down to here. What's in this section up here then? A vacuum. There's nothing up there. It would be empty space up there. Which is hard for us to comprehend, but yes. If you fill this thing with water and then tip it up, the water would come down to this 34-foot level, and above the water would be nothing but empty space with some water molecules floating around there. Some water molecules are going to escape from the surface and fly around. But other than water molecules up there, it's a vacuum. Pretty cool. Now, atmospheric pressure changes with time. One day you might have a high pressure day, then you might have a low pressure day. Low pressure days frequently result in rain. Right now, I don't know, it's cloudy right now, it's been rainy, we probably have fairly low pressure. When high pressure comes in, when the atmospheric pressure is a little higher than normal, then you typically have sunny skies, no clouds. So to meteorologists, atmospheric pressure is important to watch. In a hurricane, atmospheric pressure is very low. That's the root cause of hurricanes is low pressure, extremely low pressure. So low pressure results in rain, high pressure results in clear skies. So the atmospheric pressure is always changing, but not by a whole lot. So we can measure atmospheric pressure by taking this 36, we'll say, this 36-foot tall jar, take an average day and mark it right there on the jar with a Sharpie, and call that 30, that's your average mark. Average pressure, I think, is someplace around about 15 pounds per square inch. So you could mark that as being the place where we had 15 pounds per square inch of atmospheric pressure. Then on a higher pressure day, that higher air pressure is going to push more water up here. It'll be up here someplace. So up here might be 15.5 pounds per square inch. On a low pressure day, it'll sink down a little lower. You might have 14.5 pounds per square inch. Depends on how high it is up in this 36-foot tall jar. So you could have your own barometer. It's called a barometer, measures atmospheric pressure. You can have your own barometer in the backyard. Just get yourself a 36-foot tall jar, fill it with water, put it in a pan, put markings on that 36-foot tall jar, and you've got yourself a barometer. Pretty cool. A little bit impractical. I checked at Walmart and they didn't have any 36-foot tall glass jars. So what are we to do? If only we had a liquid that was a whole lot heavier than water. If the liquid was heavier than water, it wouldn't rise up as far. The atmosphere wouldn't be able to push it up as far. What liquid do we know of that's a lot heavier than water? What liquid do we know of that's a lot heavier than water? What liquid do we know of that's 13 times heavier than water? Yes, mercury. Aha! Mercury. A mercury barometer, if we fill this pan with mercury instead of water, my jar only needs to be, I don't know the exact height it needs to be. It only needs to be maybe about 30 inches tall. Because since mercury is 13 times heavier than water, the atmosphere can only hold up about 28, 29, 30 inches of it. This is a whole lot more practical. That's the way we use to measure atmospheric pressure. It's called a mercury barometer. In fact, to this day, even though we don't use these anymore, we have better ways of measuring atmospheric pressure. We don't use this anymore, but we still refer to the atmospheric pressure in terms of inches of mercury. If you've ever heard a news report, a weather report where they talked about, today's atmospheric pressure is 28 inches of mercury. So what's that inches of mercury stuff about? It comes from this. That's how much mercury the atmosphere can support. 15. Did I say 15? That's really low pressure. It's more like 28 on average. I'm not sure what the average is. 28, 29, something like that. I'm not certain. So we measured in inches of mercury for old time's sake. There's, by the way, another measurement for air pressure. We also measured in what's called pascals. 1 pascal is 1 Newton per square meter. 1 pascal, definition, 1 pascal equals 1 Newton per square meter. That's the definition of a pascal. So we can measure, in the metric system we measure it in pascals. In the English system we measure it in pounds per square inch. Now, he gives us a better number here. He tells us on page 271 that the average height of the mercury in the mercury barometer would be about 760 millimeters. So we might measure the atmospheric pressure in millimeters of mercury. Now, what else do we need to throw in today? I don't want to go too much further. Hey, I haven't asked any quiz questions, have I? Let's throw in one right now. Hopefully I can get in 4 before I quit for the day. I have no idea when I started this video. Could get in trouble here. Tell you what, for quiz question number 1, just tell me what number I have just circled. That's all. What number have I just circled for quiz question number 1? See, the quiz questions are not intended to check for understanding. The quiz questions are simply intended to check to see if you're actually watching the video. So quiz question number 1, write it down someplace. What number did I just circle? Now, let's see. Oh, here's a cool concept. When you drink from a straw, Paul Hewitt's artwork, of course, is much better than mine. He's got an interesting diagram on page 271. It actually took me a while to figure out what in the world that big pink thing was, and I realized, oh, it's a giant fist pushing down in the water. Yeah, if you've got a container of water, you're at McDonald's. Actually, you can't be at McDonald's anymore, at least not during COVID-19. But you used to be at McDonald's, and you're sitting there, and you've got your cup of Coke, and you've got a straw sticking out of it here, and you're sipping Coke through the straw. How do you do that? You suck on the straw. Here's the question. Why is the Coke going up the straw into your mouth? Well, because I'm sucking on it. Is suction a force? What am I actually doing? When you suck on the straw, it's natural to us. I don't even know how I do it, but if you really, really think about it, you suck on a straw, you're actually expanding the inside of your mouth. You're kind of, I don't know how that works. But maybe you're using a little bit of lung power, but you can also do it just by expanding the inside of your mouth. But what you're doing is you're enlarging the area, whether through your lungs or through your mouth. You're enlarging the area, thus decreasing the pressure inside your mouth. So up here in your mouth, and no, I'm not going to try to draw a mouth. That would be awful. I'm tempted. I'm not going to try. Oh, I'm tempted. Okay. There. Okay. There's a dude. Okay. This is his nose. That's not bad. That's not bad at all. Okay. I like it. Eyeball up here someplace. Okay. Oh, it just got worse. Hair. Okay. Well, that's pretty good. I like it. Anyway, so this dude is sucking on this drink here by expanding his mouth, creating lower pressure here. If he's creating lower pressure here, then the atmosphere is now going to be able to push the Coke up the straw into your mouth from the area of higher pressure to the area of lower pressure. So when you suck on a straw, the Coke is not being pulled up the straw. I'm sorry. Banish that from your mind. The Coke is not being pulled up the straw. No, the Coke is being pushed up the straw by atmospheric pressure. The Coke is being pushed up the straw. Hey, let's throw in a quiz question number 2 here. So jot this down someplace. Quiz question number 2. What shall it be? What is the atmosphere doing to the Coke? It is pushing. There's quiz question number 2. Just write the word push. The atmosphere pushes the Coke up the straw. You are not pulling it up. The atmosphere is pushing it up. Now, there was something else. Oh, what if we sealed this container so that the atmosphere can't get to it? Have you ever tried to drink out of a straw in a container that's sealed in some way, shape, or form? You can't do it. And nothing happens. Why not? Because you may be lowering the pressure here, but there's no atmospheric pressure pushing on the liquid. It can't be pushed up into your mouth. You cannot suck it up here if the container is sealed, unless it's one of these squishy containers. If it's a squishy container, then yes, the atmosphere will squish the container and push the liquid up the straw into your mouth. But if it's a solid container, a metal can or something, or your water bottle, if the air can't get in, then you can't suck the liquid out. Try it. You'll see that it's true. Put your mouth on the open end of a Coke bottle, old-fashioned Coke bottle, and try to suck the Coke up. It's not happening. because the atmosphere can't get in to push the Coke up if you have your mouth over the entire mouth of the bottle. Okay, I think, how many quiz questions have I asked you? I think it's only been 2, hasn't it? I need a third quiz question. Third quiz question. What's this thing right here? You're at McDonald's, it's in the drink. That is called that's called a straw. That's quiz question number 3. And I'll come up with quiz question number 4 in a moment here. I think I've only given 3. If I've given 4 already and I give you a 5th, that's okay. We're going to stop here and continue with part 3 next time. So, on that note, I suppose I should say bye. And that will be quiz question number 4. What word is written at the end of this video? It's the word bye. So that's quiz question number 4. So write down those 4 quiz questions. 1, 2, 3, 4. In the body, type it into the body of the email and put the subject line of CI or perhaps CLS physics 14 part quiz 14 part 2 or whatever it was I said earlier. You saw it. All right, thank you, and we're done for now. I'll get part 3 to you as soon as I can.